Hi, everybody. I'm very happy to be here with you today at the Global Innovation Forum. So my name is Barbara. I'm the founder and the CEO of Interstellar Lab. And we're going to talk about living in space and how to use space technology back on Earth so we can learn how to live more sustainably. So Interstellar Lab, the problems we're trying to solve, basically, there are two different problems. One is on Earth, and it's basically that we have 10 years to transition to regenerative environmental solution. There is a huge need that we right now on Earth install and have a more holistic approach when it comes to food production, water treatment, and waste management. So there is a huge need to develop sustainable, durable, low carbon emission habitats, and also food and water system, as I explained. And if you think about Mars, and if you think about living on Mars, okay, this is not going to happen, like right now or tomorrow. It's going to happen actually quite soon as well. Like in 5 years from now, we'll actually send the first rocket to Mars, the first Starship, and in 10 years from now, we'll probably gonna see the first humans going to Mars. But the dream of becoming a multiplanetary species is not gonna happen if we don't test before we go over there. Closed loop system to produce the food, to recycle the air, to recycle the waste, to recycle the water, so humans can live sustainably and separated from the Earth. And so if you think about it, it's very interesting because the problems that we're facing on Earth are actually very similar to those that we will face on Mars in 10 years from now. And in a way, the system and technology that we can use for Mars can help us on Earth. So what we do at Interstellar Lab is that we develop station that we call Ebios, so experimental bioregenerative station. Those are closed loop station, completely sealed and environmentally controlled. And they're built as different module and closed ecological system. So inside the station, we recreate an ecological system for humans to live, to have access to food, water, and to recycle all the waste. So each station is designed, as you can see right now, as a combination of different modules. So each module, we call them flowers. They organize with 4 different units. The one unit is the habitat section, as you can see on the top, and 3 domes, 2 dedicated to food production. So one is the aeroponics dome, one dedicated to the greenhouse, a subtropical greenhouse, and a third one dedicated to water and waste management. Each dome is completely environmentally controlled with its own temperature, its own level of humidity, and very different atmospheric condition. If you think about it, if you want to increase the production of crop in the aeroponics dome, we will need to boost the CO2 level and to manage the temperature differently depending on the plant's need. And that's not the case in the habitat. In the habitat, you don't want to boost the level of CO2 because habitat, this is where humans are. And basically what you want to do is to have a very good balance between the oxygen level and the CO2 level. So it's very important that the control of the atmospheric, the temperature and humidity is done at each dome level. And then you have an integrated system, meaning that of course, we recycle the water and we recycle the waste at the dome level, but then there is part of the water, what is called black water, that we will go to the water and waste system, where we will basically recycle the water and turn it potable again, or put it into the agriculture units, and we will take the waste and using aerobic and anaerobic system, we will turn the waste into nutrient solution for the greenhouse. And so basically, so each dome, as I said, has a specific condition. So this is a view of the layout of the aeroponic dome. So inside the aeroponic dome, you have what we call the A-frame aeroponic system. So aeroponics is a system that is feeding plants by spraying high pressure water. So it means that you use much less water than traditional agriculture. The shape that we gave to the A-frame is very space efficient, because basically by having this A-frame shape, we allowing a very, growth ratio between the growth surface and the floor surface area. So we designed the system and we integrating it with the LED lighting system that is designed to really bring to the plants the amount of light ppfd that the plants need, that each plants need. And the plants are selected by a crop selection algorithm, and I will tell you a little bit more about it after that. The greenhouse, so the greenhouse is the subtropical greenhouse, same. It has its own atmospheric condition, humidity and temperature condition. In the greenhouse, you will find subtropical trees, dwarf trees. The purpose of the greenhouse is not to be as efficient as the aeroponic system dome when it comes to food production. The purpose of the greenhouse is, okay, to grow some of the food, especially fruits, because it's hard for fruits to grow in aeroponics, but it's also to fulfill all the psychological, some of the psychological needs of humans, trying to reconnect humans with nature. And we know that the connection between humans and nature is very important for the well-being, for the psychological stability. And so the purpose of the greenhouse is at the same time to grow some of the fruits, but also to offer a garden for humans so they can find back their equilibrium. Because try to, put in lockdown without access to any plants or any nature, humans will go bananas very quickly. So the last dome is the water and waste system dome. So as I said, in this dome, it will be part of the water and waste system. The rest of the system will be integrated in each dome. We're going to use aerobic and anaerobic at the beginning to turn organic waste into nutrient solution. And we're going to use different systems to purify the water. Right now, we're looking mostly at UV disinfection system, activated carbon filters, and a little bit of reverse osmosis as well. So combining different systems so we can purify the water. But there are a multitude of options on which technology we can use. So actually, we're going to, in the coming months, we're going to test a different system to figure out what works best with our water. And so to design such a station, you need to do a lot of simulation before. So what we've been doing over the past month in the company is to develop what we call the Ebios simulator. So it's a combination of a stoichiometric equation, so scientific approach, and algorithm and reinforcement learning artificial intelligence, where we basically, as you can see here, you put the requirements. You put the requirements that you need. Hop small video problem, but it's going to be back. So you put the requirements that you need for a mission, and basically you enter so the number of people, the location, how much diversity do you want in the food, what are the preferred technology that you want to put into a station, if it's aeroponic, if it's a subtropical greenhouse, and if you want to cover all the nutritional requirements, if you want to get some customization. You can choose, as I said, the crop diversity. And here you can, if you want more specifically, you can decide, what plants do you want to put inside, and how do you want to maximize the nutritional requirement. Then you run the algorithm. So our algorithm is basically providing a solution of crop selection. So it selects crops based on the number of people, based on the target for the nutritional requirements, and then it organizes all the crops between the aeroponic and the greenhouse, giving us the overview of what each crop is going to bring over time in terms of the nutritional value, in terms of omega-3, in terms of sodium, of zinc, vitamin E, of course, carbohydrate, protein, fats, all the important stuff. But so we're really trying here to select all the plants that we will need to fulfill all the nutritional requirements. And so by using our artificial intelligence, basically, we are able to customize and to tailor it a little bit more, and to make the crop selection. The crop selection is very important. This is the first step to build a station, because when you build a station that is completely into a closed loop system, you need to know all the crops that you're going to select, to modelize them and to estimate how much O2 and CO2, water and light they need, and then you can design the hardware. So at the core of everything is really which crop you select and you're gonna grow that have a huge influence on how the station is going to behave. So that's why this part is very important. And also something to understand is that the modelization of plant growth over time, when it comes to state of art right now, there is still a lot to be discovered and a lot to be done. So that's why we need, you know, reinforcement learning basically, and artificial intelligence that we're going to plug into real-time data into the station to further optimize our crop selection. So if I move a little bit like down the road on the software side, basically, as soon as you selected the crops and you run the first simulation, then you can upload into the second algorithm, basically, the crop selected. So then the algorithm is basically modelizing all the chemical, biological interaction inside the station. So we can basically understand what's going to happen when the station is going to be built. And so what you can see and what the algorithm is what the software is showing is basically the evolution of oxygen, CO2, the evolution of the different tank when it comes to the water needs, to the nutritional needs. And from each dome, basically, what we develop is the simulation tool so that can help us predict what's going to happen. So then you can run different scenarios, upload different crop selection, and you can see that depending on the crop you selected, basically, the outcome is very different because some crop reject more O2, some crop needs more CO2, and then there is this balance that you need to find. There is the level of temperature that you need to play with. That had a lot of, you know, impact on how to manage the entire station. So the next step for us is basically to plug in our software and simulation into real-time data. So that's going to happen in the 6 coming months. That's what we're working on right now. Basically, what you can see right now is the dashboard of the future station. So as I said, we're going to the third part of the software that we're doing is so to connect all the simulation that I've shown you before to sensors and data that is straight coming from the station. And then as soon as we get this data coming from the station, then we can plug in and put it into our simulation software and see first how good or bad were our prediction. So validate the model and update the model. But also it will help us and, you know, have a very active control of what's going on into the station. So if we can see that in the greenhouse, some of the level of CO2 are declining and that we need to boost it up. So based on our prediction, we'll be able to know that before and then to trigger the CO2 scrubbers, you know, before, I mean, it's not going to be too late, but to anticipate. So that's very important. That is this entire part of, at the same time, simulating, getting the artificial intelligence, predicting what's going on, but also then you have all the control system that needs to be plugged in with the sensors. And that's going to be the next step for us. So that's how the dashboard and how you're gonna see that. But it's very important to keep like here the real time, but also to see the prediction, to have a very active control of the station, and to be able also to be less dependent from mission control. So it's one of the main problems for the International Space Station that it relies a lot on humans on the ground that are, you know, maintaining the system. And if you talk to astronauts, what they're gonna tell you is that they spend most of their time basically fixing what's happening inside the station. So we took their feedback into consideration to developing a software tool that will enable us to manage and to predict much more in advance. So people inside the station, they basically don't spend all the time fixing and, you know, taking care of CO2 scrubbers and oxygen. So what does it mean to live inside Ebios, to live inside the station? So station are, so the idea for us is it's to develop a place where you know, the general public, but also scientists and astronauts can come live and experience. For scientists, it's going to be to run their experimentation. They will have access to, of course, our platform data, and we're looking forward to collaborate into, you know, advancing more into developing a regenerative solution. For astronauts, it's obviously a place for astronaut training because it's a completely closed loop system. So you're not connected with the outside world. So you need to learn how to, you know, it's a little bit like the Martian on Earth. And for the general public, for us, it's very important because it's a way to show to people and to give them hope that there is a possible future where everything can be recycled, regenerate, and it's a future where technology and nature mix, and where human is not harming the environment. So it's really important for us to show that technology is our friend in making this happen. What's going to happen in the coming months? So we're looking forward, coming months, coming years. We're looking forward to install several stations on this planet, on Earth. So probably the first one's going to be in California and in Paris. Paris next to Disneyland, California in the Mojave Desert. We want to put a second one in United States, most probably in Florida, next to Kennedy Space Center, and also to Epcot, again, Disneyland. We're looking into Saudi Arabia and Desert Zone. We're also looking into Japan for 2023, and there's probably going to be another station that we will put also in a very cold environment. This is a render of a station in a greenery. We had a lot of renders in station on Mars, but this one is on Earth. And what's new, what's coming for us right now is the developing a food production system that is a very efficient. So basically, as a first step before building a station, we've been developing a baby dome that we're going to put in Paris in the coming months. Probably in this place here, which is a big center of innovation in Paris. So this is a render of baby dome. We've been doing a big iteration on the design. So very soon you'll see new design. But in Q1, so between January and March, we'll have our first dome working. So baby dome is a sealed biodome. So it's very similar to, it's actually a small scale food production dome combining our aeroponic system and our subtropical greenhouse. And it's completely closed. So exactly as the same system that I described to you before. And it has its own closed loop water treatment system with an air water catchment system. So it means that inside the baby dome, so I'll show another graph just after. But inside the baby dome, basically, we're gonna catch water back that is in the air, so humidity, and we're gonna put that again into the system. So it means that we're closing the water loop, so we require much less water than traditional greenhouses. It also had its own control atmospheric and air system, so meaning that we can play with this level of CO2 and O2, and actually, it's very interesting because the dome, how it's working, it's breathing air from outside. So baby dome is taking a deep breath, so atmospheric air from outside, and then we look at the level of CO2 and O2, and because we are in a food production dome, we want to boost the level of CO2. And so to do that, instead of putting tanks of CO2 and pushing CO2 inside the dome, to do that, what we did is that we put CO2 scrubbers that are sucking CO2 around baby dome. So baby dome is basically taking CO2 out of the atmosphere and to produce food, and it's generating oxygen. So that's pretty cool. It's like it's a condensed forest into a biodome that is also producing food and reducing the emission of CO2. Inside the baby dome, you have a set of sensors. As I said, what is very important for us is to really understand what's going on inside. So we need to put a lot of sensors that we're gonna plug into our artificial algorithm prediction, artificial intelligence prediction algorithm, and then to compare what's going on and to optimize and to control. So if we look at if you look a little bit more into the design, so it's composed of a composite base. So this is what you see right now. So it's a high performance shell, which has very high insulation purposes. And then inside, basically, you have a flexible layout. So we can put the different components. Here, this is the air system, the water system, and all the nutrient dosing system that we put inside the base. Then we have a platform that is put on top, so we can have access to the system. Then you have here, which is the inorganic substrate for the greenhouse, which is composed of also of hydrogel with a intensive drainage system. And then on top, we put the A-frame aeroponic system. Then you can see the plants, so tropical trees and dwarf trees, and the aeroponic culture, which is like much more focusing into, as I said, intensive food production. On top of the baby dome, you have the inflatable membrane that we developed ourselves. It has very high insulation properties, and all the dome is completely locked by a airlock system to control the access to the dome. So that's the baby dome that's coming in a few months from now. For us, First, it's a prototype for a sustainable food production system. And if you think about it, it's very interesting to see how, by thinking of designing a system so we can live on Mars, we came up with a station design where basically we understand how to live on Earth in a regenerative way. And by the need for us right now to test our system, we developed this food production system. This food production system, which reduced the land need by a factor of 100. I mean, Babydome is able to produce all the vegetables and fruits that are needed for a small family in Europe, basically. So having a Babydome in your garden, you will not need to buy any food, any fruits, or nothing from, from the stores. Also, a good thing is that it's a subtropical greenhouse, so it means that no need to fly your avocado or your mango. You can grow it in the Babydome. But basically, those are the figures. To grow enough food for a small family in Europe, you need around 4,000 square meters of agricultural land. Babydome is around like 30 square meters. So it means we drastically reduce the land need, and we allow to give more land back to the wilderness, which is exactly what we need right now on Earth if we want to help, changing what's happening right now with climate change. Babydome, because we're using aeroponic system, it drastically reduced the water need. As I said, we have an air water catchment system, and we recycle the water inside. So the dome doesn't need to be plugged into a water system. We have a tank, and then we reuse the water. Babydome captures CO2. So as I was explaining, it breathes in the atmospheric air, and then it pumps CO2 using CO2 scrubbers. So it pumps CO2 and it rejects O2. And Babydome also foster biodiversity. One of the main problems we have right now on Earth is that 6% basically, six species represent 60% of all the food that we are eating. So the problem with biodiversity is not only that we are destroying land and destroying biodiversity, but it's also that the food that we eat is not diverse, and so we're losing species, and we're decreasing the biodiversity by not having a more a better diet. And thanks to our crop selection, again, because this is one of our parameters, we're increasing the biodiversity into the Babydome. So that's Babydome on Mars. So we're looking forward to, there are going to be iteration, like between this first version of Babydome that's going to come in 3 months and the version that we're going to put on Mars. There are going to be a lot of differences, and especially when it comes to the membrane and how we got, protection from the solar radiation, definitely. But the concept in the first part and inside how it's working is going to be very, very similar. So we're looking forward, and we really want to, to be the first one who gonna put a little bit of life on the red planet, and we're looking forward to it. So thank you so much. It was a pleasure presenting Interstellar Lab. If you want to join us and help us build a future full of life on Earth, on Mars, and beyond, feel free to reach out.